Hi, I'm Marcel Oliveira from the Federal University of Rio Grande do Norte in Brazil, and in this talk, I will present a paper entitled Empower SysML-based Software Architecture Description with Formal Verification from SysADL to CSP, which is a result of joint work with my colleagues Fagner, Thais Batista, Everton Cavalcante, Jair Leite, Flavio Oquendo, and Camila Araújo. First, let me bring you to the context of this paper. As we know, the software architecture has an important role in its development because it has an important contribution to achieve the functional requirements and an acceptable final software quality. In this context, we have the architectural description languages, the ADLs, which are used to describe these architectures. So, using ADLs, we obtain more concrete descriptions that can be used to describe design models and execution models. ADLs also offer support to documentation, maintenance, evaluation, and evolution of the software. However, most of ADLs do not have a formal semantics and an integration of their supporting tool with a formal verification mechanism. Some of them may even have a formal semantics, but lack such an integrated verification environment. For this reason, one of the main difficulties in software system designs is to verify the correctness of the architecture. That is, if the architecture fully complies with the established requirements. It's also important to say that if this analysis is done during design, it will be able to identify errors, inconsistencies, and other problems very early in the development process. In summary, the main advantage of adopting a formal approach is to be able to precisely determine if the architecture satisfies the properties of interest. As a matter of fact, we have in the literature some works that formally define ADLs as a means to guarantee consistency and correctness of the architecture. One of the ways to validate these properties is simply to generate source code or somehow generate an executable model and simulate the architecture. But this simulation constitutes no proof that the architecture always satisfies the properties of interest. This proof can be obtained using a theorem prover, but this already requires the formalization of the language, and obviously it also requires interaction with a theorem prover, which is a considerable effort. We strongly believe that this would discourage the use of the methodology by software architects. So, based on these considerations, we decided to go for the third option, using model checking to achieve a formal verification in a completely automatic way. Our principle in this project is to provide a completely automatic formal verification that is integrated to the ADL supporting tool and hides all formal notation from the architects. In this project, we work with SysADL, a SysML profile that can be used to express architectural descriptions using abstractions well known to the ADL community that combines ADL's typical constructions with the standard SysML diagrammatic notation. In this paper, we basically provide a formal semantics to SysADL, and based on these semantics, we provided an automatic formal verification of SysADL models. For that, we integrate to the SysADL Eclipse-based supporting tool, SysADL Studio, a plugin that enables this automatic formal verification of SysADL models. It's very important to say that this verification is completely transparent to the user, who needs no knowledge of the formal notation used in our approach. Our approach will allow the following development process. The architect uses SysADL Studio to specify the structural, behavior, and execution views of the system architecture. Once the model is complete, it can very easily ask the tool to formally verify the architecture. Our tool will use the definition of the formal semantics of SysADL to generate a CSP specification with assertions which will be sent to FDR, the main CSP model checker. FDR will then verify the assertions and give a feedback to our tool. Finally, our plugin will return the results to SysADL Studio, and these results will be presented to the user in a very friendly way. In the paper, the application of SysADL formalization is illustrated with a room temperature control system. In this simple example, the automatic formal verification demonstrated that the architecture has no deadlocks and no live locks, traditional desired properties of concurrent systems. It also demonstrated that the behavior described in the behavior view is respected by the executable view. In the example of this slide, it's trivial to see that the equation of the constraint Fahrenheit to Celsius EQ in the left-hand side is indeed respected by the executable Fahrenheit to Celsius EX. Nevertheless, bear in mind that this correspondence is not always trivial. An interesting case was raised during the development of this case study. Our approach identified a miracle, that is, a specification that is simply impossible to be implemented. That's because the architecture has a component that transforms temperatures in Fahrenheit to temperatures in Celsius using the correct expression. Nevertheless, both temperature units are defined as the same range of integers, from 0 to 100. For this reason, it's impossible to provide an implementation that satisfies both the transformation predicate and the type restrictions for all possible Fahrenheit temperatures. Notice in the slide that there is a range of Fahrenheit temperatures from which the transformation predicate takes us to Celsius temperature that are outside the typing range. This sort of problem is also identified by our approach. We have also been able to verify safety and liveness properties of our architectures. For instance, in our example, we have verified that the cooler and the heater cannot be turned on at the same time, and that if no presence is detected in the room, then its temperature is always adjusted to a predefined temperature. To conclude, we move on to the work still to be done in the context of this paper. First, we have already done an analysis of the scalability of the approach. We were happy to see that as we increased the number of sensors and actuators up to 1,000, the verification time growth proved to be linear. We are currently working to allow the definition of functional requirements, safety and liveness, using SysADL. Next, we also intend to implement traceability mechanisms to allow developers to identify any problems without the need for knowledge of the formalization involved. As an optimization, we will integrate our tool with a SAT solver to analyze Boolean conditions in a more efficient way before applying our approach to further case studies in the context of smart cities in which our project is inserted. Finally, we will formalize the semantic rules and move on to allow the verification of SysADL dynamic configurations and mobile processes. In summary, this paper presents a CSP-based approach to support the automated formal verification of properties specified in SysADL, a SysML-based ADL. The solution relies on empowering SysADL with model checking by combining the CSP process algebra and the FDR4 model checker, besides providing semantics for SysADL diagrams. With the proposed approach, it was possible to verify properties related to deadlocks, live logs, miracles, and consistency among the different viewpoints of the specified configuration-based behavior. The concretization of the approach in the Eclipse-based SysADL Studio tool allowed validating it in several scenarios, including the example presented throughout this paper. The same approach can be applied to other SysML-based ADLs to formally verify architectural properties. If you are interested in the details of this approach, I invite you to read more details in our paper. Please also feel free to contact us if you need. That's all for today. Thank you for your attention. Stay safe. Bye-bye.